And here's the injector port. So the molecules come in, and they go around and around and around and around and around, and then out. Circulating fan, which is keeping this oven at a constant temperature. The column is hanged right there, and then there's insulation here as well. So what's the reason for the heat? Why do you got to keep the oven essentially at a certain temperature, and it's got to remain at a constant temperature all the time? Because otherwise the compounds just sit there. The hotter they get, the faster they want to move, and then they move out of the machine. Now again, the temperature is essential, so you got to keep that temperature constant, and they really have to prove that as well. So here's the capillary column. You have the stationary phase. All right, so there's the outside of the column, and then there's what's called the stationary phase. Now, the stationary phase is this viscous liquid. All right, so what happens is the compounds go in, they go through this column, and inside the column is this liquid, all right? And what it does is slows down each compound. And this is getting a little bit complicated, but essentially each compound has a certain affinity for specific column phases, all right? So the lab has to get the right phase, meaning there are certain columns that are not good for ethanol testing. They're good for other things, but not for ethanol. And you got to get one that's actually good for ethanol, one that ethanol likes. So the compound goes through, and ethanol is going to hang out here on the stationary phase for a certain period of time. It's just going to sit there. And it would sit there forever unless the carrier gas finally pushed it through and was heated up to a certain temperature. But for each column, it's known, there's supposed to be a known period of time that this actual compound stays there. It stays there, and each compound is going to stay there for a particular period of time. So ethanol is going to be there for, let's say, 1 minute and 3 seconds, all right? Or 1 minute and 30 seconds. Isopropanol is going to be there for 1 minute and 50 seconds, all right? And that's how we figure out what is the compound. We're going to know when it's coming out of the capillary column. Now the column goes up into that's the injector. All right, so as I was talking to you before, there's a moving phase, there's a stationary phase. The compounds go in, they sit there on the stationary phase, and they all come out at a certain period of time. And then if it comes out at 1 minute and 30 seconds, then you know it's ethanol. Okay? It's called elution. So it's eluting at a certain period of time. There's a known retention time. It's retained in that column for a specific period of time, and then it elutes, it comes out. All right, now here's the important part about how the science has to work. It's just a machine. It's a stupid machine. It really is. It knows nothing until you teach the machine what ethanol is, okay? And you have to introduce into the machine what ethanol is by using what's called a certified reference material, all right? Certified reference materials are something that you get from the National Institute of Standards and Technology, NIST, all right? And it's NIST traceable, meaning there's documents that come with it that say, we guarantee this is ethanol, all right? There's no problems with this. Here's the standard. You put it into your machine, and your machine, you can tell your machine that this is ethanol, and when it elutes, comes out of the column, and the detector finds it, we're guaranteeing essentially that it is ethanol. So, okay, if it's NIST traceable, that's the highest standard. You can then introduce it to the machine, teach the machine what ethanol is when it comes out. Good. All right, 1 minute and 30 seconds, we know it's ethanol. Now, anything that comes out of this machine at 1 minute and 30 seconds, it's going to be ethanol, most likely. And then you want to create what's called a calibration curve. So, all right, how do we know what's 0.01 and what's 0.15? Well, you got to teach the machine how much ethanol, what it looks like essentially to have a 0.15 BAC, what it looks like to have a 0.05 BAC, and create a curve. And it doesn't actually curve, it's a straight line, all right? And you should have at least three points, 3 data points, which should be like an 0.5, a 1.0, and a 2.0 minimum. But you can have 5 data points, 10 data points, as many as you want to make sure it's as accurate as possible in calculating the amount. Separation mix. So there's something called a separation mix, which essentially is teaching the machine also to identify other compounds that are typically coming out in human blood. Maybe there's isopropanol, maybe there's methanol, acetaldehyde, okay? And you got to teach that machine to be able to differentiate between all of those compounds. And again, you're introducing into that machine a standard, and you're teaching the machine, hey, this is what acetaldehyde looks like, this is what isopropanol looks like, and if there's proper separation, you're going to see the difference. And isopropanol is going to come out in 1 minute and 50 seconds. Acetaldehyde's 2 minutes, let's say, or 30 seconds, whatever the column does. And then after that, you do a verifier. So before each run, you want to put in a control. You want to actually put in a known ethanol. Make sure that the machine's doing its job properly. It can detect ethanol. You put in the unknowns, all the client samples, essentially, all the defendant samples. You test them. And then at the end of the run, you have a verifier. You put in another known sample to see, again, at the end of this run, can that machine tell where ethanol's coming out? All right? The best way of doing it is dual column testing, so you actually have two of these columns set up in the machine as opposed to one. That is the best way to do it. Most labs do not do it that way. Simple saying, garbage in equals garbage out. So if the lab can't prove that they did this properly, if they didn't set up the calibration properly, if they didn't do the controls, if they didn't do the verifiers, it's not a good test. And they can't say to a degree of scientific reliability that this is actually alcohol. So as I talked to, and the one thing that I wanted to mention, I'll get that one. All right, so calibration curve. Here's an example of calibration curve at 1.0, 1.5, 2.0, 3.0, and 3.5. Can anybody tell me what the problem would be if you didn't do a calibration curve that went down to, let's say, a 1.0, an 0.1, I mean?
Are you saying if you didn't go below a 0.10?
Yeah, let's say you didn't go below a 0.10, all right?
Yeah, because the limit is 0.08.
Exactly. So how are they going to reliably tell you that this quantity of ethanol, they're going to be able to identify, but how can they tell the quantity is an 0.8 if they don't have a calibration curve that has its lowest point below an 0.8, right? And then if you have commercial truck drivers, it's an 0.4, and then if you have miners, it's an 0.1. So you got to go down to 0.1 and potentially up to at least a 0.15 because that's where ignition interlock devices start to come into play, right? And again, the calibration curve should be done before each run. You don't use a historical curve. So you don't go back to the one you did a week ago and actually say, all right, well, computer, let's utilize that curve from a week ago to quantitate today. No, you got to do it each time before the run. Blanks. So I was talking about how to eliminate carryover, how to make sure there's no contamination. The lab should run a blank between each unknown, right? So defendant A gets tested, and then you put a blank between defendant A's blood sample and defendant B. The blank is essentially deionized water, so there should be nothing that comes out essentially, right? And if there's carryover, then what you'll see on this blank is maybe ethanol, right? And then you know that there's some carryover. There's the testing process is compromised. If you don't do that, you can't prove that there's no carryover. But laboratories won't do that because it's an extra expense and it's an extra time creating the blanks, typing them into the computer. All right, so it goes in, goes to the column, and out through the detector. Here's the detectors. There's a close-up view of it. This is the flame ionization. This is the flame tip. You see how small it is. Here's a quarter. Shows you how small it is. And each substance that comes off gets burned up. Okay, again, the amount of the compound, the amount of the molecules that come out that determines the quantity, all right? And then, with mass spectrometry, there's a different method that's being used. So if there's one thing I want everybody here to take from this,